Hi everyone, we are the Clean team, and this semester we created an autonomous door handle disinfector. So the objective for this project was to design an autonomous device that periodically disinfects a door handle using UV light. Our motivation for this was because after the COVID-19 outbreak, there was large demand for ways to sanitize public spaces more efficiently. Door handles are one of the most common ways to spread viruses due to the large amount of people who use them and how rarely they are cleaned. This design will allow for a door handle to be sanitized regularly to prevent the spread of COVID-19. Now, as shown in the picture, there will be a rail mounted to the handlebar using a clamp at the opposite end of the push bar to hold the rail into place. A 3D printed casing holds all the components to slide back and forth on the bar. The casing is attached to the bar using a glider on the rail. There are wheels on the bottom of the casing so that the casing can roll with ease. The motor is placed inside the casing with a tire on the motor shaft as the force of movement to move it from side to side. There is a removable front wall located on the bottom half of the casing for the UV LEDs to sanitize the handlebar. There's also a motion sensor mounted as an interrupt to stop the device if someone approaches. A microcontroller is used to implement simple logic outputs to communicate with the Arduino. And also, user can communicate with the device through a Bluetooth interface that is implemented.
So here we can see the block diagram for our project. It starts with the programming that's done in C here on the left, which uploads to our Sp22 microcontroller through a snap debugger. Once the program is on the microcontroller, it has a few applications. So the first one is that the microcontroller connects to an Arduino that's located on the device, and then this Arduino is able to utilize Bluetooth to speak to another Arduino that can then control the device remotely. The microcontroller also connects to a motor driver that runs the motor, and here on the right we also have a proximity sensor that acts as an input to the microcontroller. So if somebody were to approach the door, the proximity sensor gets triggered and the microcontroller stops the motor. And last, we have the LED array that actually sanitizes the door handle that's being controlled by the Arduino. So for our hardware design requirements, we have a few key elements. First being the UVC LED lights. So with 20 seconds of exposure time, this is what's used to sanitize the door handle. We also have a Cori motor, which is used to move the encasing across the rail. We also have an outer case, which is a 3D printed design done in SolidWorks. We have a proximity sensor that has detection from 15 to 30 feet to sense if somebody's approaching the door. We also use the light sensor to ensure that the lights were in fact turning on. We also have a Bluetooth module that can communicate that information back to make a closed loop system. And last, we have the rod and bracket assembly that actually allows the casing to glide across the rail. So throughout the semester, we ended up making a few changes on the original hardware design. The first change that we made was that the LEDs that we used, the first set originally didn't have a data line, which is something that we needed to control the specifics on the LED, so we got a new set of LEDs. We also used a different motor than we originally planned for, so we switched to the FIT0186 motor because it actually had an internal Hall sensor whose data we could use to confirm the device actually did run when intended to. And last, we discontinued the use of the light sensor. So in this next video, you'll see the mechanical functionality of this device, showing that the motor is gliding the encasing across the rail.
Our software design requirements are based around a Sp22 microcontroller. The Sp22 was intended to use timers and interrupts to control a motor with pulse width modulation as well as an LED array. We also use timers on the Sp22 to handle waiting between activations and the duration of each cleaning cycle. Our plan also included Bluetooth integration for wireless data transmission with the device via an app interface. The Bluetooth is implemented as a master-slave pair of Bluetooth modules connected to Arduinos. The module on the user end is configured in master mode and initiates the connection with the slave module on the sanitizing device. The slave can receive data from the user and then set a timer value on the microcontroller, or it can send diagnostic data back to the user.
A Sp32MX microcontroller with 28 pins is used to coordinate the signals throughout the system. One of these signals is an input signal from the PIR proximity sensor. When the sensor detects movement within 15 feet, it sends a logical high to the microcontroller. The microcontroller reacts by cutting off all of the modules that are currently active until there is no more motion detected. This is implemented through an external interrupt on the input pin. Two other external interrupts are configured on an additional 2 input pins to receive signals from the Arduino when communication is required. 3 different timers were configured to coordinate timed actions and events throughout our system. The main timer is a 32-bit timer that is used to implement the periodic activation of our device. When this timer reaches a certain value, which is determined by an adjustable global variable, it will activate the movement and LED sequence on the device. The motor is activated by sending a PWM signal to one of the 2 inputs on the motor driver. This signal is generated using the microcontroller's output compare modules, which implement about a 20% duty cycle. The OCM modules are enabled during the movement sequence, which is triggered by the main timer. An additional 16-bit timer is used to create the 20% duty cycle of these PWM waves. Finally, another 16-bit timer is used to coordinate the communication between the microcontroller and the Arduino. This video demonstrates the motion and LED sequence that is periodically activated on the device. For this demonstration, the main timer is set to 15 seconds. Every 15 seconds, the motor is activated first in a counterclockwise direction as the device moves across the length of the door handle. The motors then stop for 5 seconds and then turn in a clockwise direction to return across the handle again and back to the starting position. The LEDs are activated at the beginning of this sequence so that the disinfection can occur as the device moves.
The mechanical system runs pretty smoothly, with the motor being able to carry all of the device's weight, including the battery on top. It's slightly unbalanced, which is due to the spatial tolerance in the screws attached to the rail. We also found that the motor would need an increased PWM to account for tension between the rail and the wheel. The LED arrays are synchronized with the motor and will turn on while the motor is running. The only issue we had was that the Arduino used to program the LEDs needs to have a continuous power to not lose any of the code on the Arduino. The 3D casing of our device can also contain all of the wiring except the power source and is designed with removable walls for ease of access to the wires. Our device successfully communicates between a PIC32 and microcontroller and an Arduino. We were also able to have a working Bluetooth transceiver where it's able to transmit data, but not large packets of data that can be used to communicate between the device and the user.
In our design, we faced several different challenges both mechanically and electronically. Keeping our tire on the rail proved to be more difficult than expected. Although the system was attached to a glider on the rail, the glider only had 2 points of contact for us to screw our device onto. We also had an issue with the bracket of the motor turning outwards. Another challenge faced over the course of the semester was the power source. The battery we used originally became drained to the point that it would take days to charge it again. After we received another battery, however, we did not have this issue. On the software side of things, there were several challenges with using the PIC32 microcontroller's UART pins. Although not shown on the slide, one of the major issues with our device was the wiring. We had used 2 solder chips which had at one point worked with our PIC32 code, but after assembling the device, something went awry. After frying several PIC32s and a snap debugger, the team rewired the entire circuit on a breadboard and used its power supply in order to demonstrate the proof of concept. We also ran into several issues with implementing Bluetooth in our device. We did get the Bluetooth transceivers to communicate, but unfortunately we were not able to get the Bluetooth into our final proof of concept as shown in this next video. As you can see in this video, our motor runs on a timer and shines the LED lights across the door handle. The motor will then stop and the device will move back the other way. The proximity sensor is covered with tape in order to prevent it triggering and stopping the motor for demonstration purposes. Overall, our team worked together to design and build the autonomous door handle disinfectant system. Although there were a couple of hiccups along the way, we were able to demonstrate our proof of concept. The code for the individual components, such as the timers turning the LEDs on and off with the motor's motion, all worked successfully. The proximity sensor also successfully paused the entire system when triggered by motion. There are several aspects of the project that can be addressed in the future, such as troubleshooting the wiring and getting the LEDs to work without the Arduino being connected to the laptop. Thank you for listening to this presentation, and go Tigers!